Welcome back to Science with Sleepy, where curiosity drifts like starlight, and tonight's journey stretches across 2 full hours, because the universe of artificial intelligence never runs out of wonders. Imagine the lights dimmed low, a gentle hum of ambient sound behind my voice, and your favorite blanket pulled close as we drift into one of the most fascinating questions about modern technology. Picture this. You ask a computer to recognize a cat in a photograph, and it does. You show it thousands of pictures, and it gets better and better at finding cats. But here's the remarkable thing. Nobody programmed it to recognize cats. Nobody wrote code that says, if you see whiskers and pointy ears, that's a cat. Instead, the computer learned. It figured out what a cat looks like all by itself, just by seeing examples. This isn't magic, it's not science fiction. It's happening right now, all around us. Artificial intelligence systems are learning to drive cars, translate languages, diagnose diseases, and even create art. But how? How does a machine, which follows instructions precisely, learn something new? How does it get better at a task without being explicitly told what to do? Tonight we're going to explore exactly that. We're going to discover how artificial intelligence actually learns. We'll journey from the simple idea that machines can improve through experience, all the way to the complex networks of artificial neurons that power today's most advanced AI systems. The story begins with a simple question. What does it mean for a machine to learn? When you learn to ride a bike, you practice, you fall, you adjust, and eventually, you get better. When a child learns to recognize animals, they see many examples, notice patterns, and gradually understand what makes a dog different from a cat. But machines don't have bodies to practice with. They don't have eyes to see with. So how do they learn? The answer lies in something remarkable. Machines learn by finding patterns in data. They learn by making mistakes and adjusting. They learn by processing thousands, millions, or even billions of examples, and gradually figuring out what matters. It's a process that's both beautifully simple and astonishingly complex. As we drift through this 2-hour exploration, we'll discover how neural networks work, those simplified models of the brain that power modern AI. We'll learn about training, the process where AI systems see examples and get better. We'll explore backpropagation, the elegant algorithm that allows machines to learn from their mistakes. And we'll see how different types of learning enable AI to do everything from recognizing faces to playing chess. The study of machine learning is one of the most active areas in modern science.
Every year, new techniques emerge.
New capabilities are unlocked, and our understanding deepens. But the fundamental question remains: how does a machine learn? What's actually happening inside those circuits and algorithms? This question touches on some of the deepest mysteries in science. It connects to how our own brains work, to the nature of intelligence itself, and to what might be possible in the future. As we explore this question tonight, we're not just learning about computers. We're learning about learning itself, about how knowledge emerges from experience, and about the remarkable ways that simple rules can create complex behavior. So settle in, let your breathing slow, and let your mind drift with me into the world of artificial intelligence. We're about to explore how machines learn, how they get better through experience, and how they discover patterns that humans might never notice. The journey begins now, and it will take us from the simplest concepts to the most sophisticated systems, all explained in a way that anyone can understand. Chapter 1: The Foundation of Learning. To understand how artificial intelligence learns, we first need to understand what learning means for a machine. This might seem like a simple question, but it's actually quite profound. When you think about it, most computers don't learn at all. They just follow instructions. You write a program, and the computer executes it exactly as written, every single time. But learning systems are different. They change, they improve. They get better at their tasks over time. Think about a traditional computer program. If you write code to add two numbers together, it will always add them the same way. 2 plus 2 will always equal 4, no matter how many times you run the program. The program doesn't get better at adding. It doesn't learn new techniques. It just does what it was programmed to do. But imagine a program that's trying to recognize handwritten digits. At first it might be terrible. It might confuse a 3 with an 8, or mistake a 7 for a 1. But then something remarkable happens. You show it thousands of examples of handwritten numbers, and it gets better. It starts recognizing 3s correctly. It stops confusing 8s and 3s. It improves, not because someone reprogrammed it, but because it learned from the examples. This is the fundamental difference between traditional programming and machine learning. In traditional programming, humans write explicit rules. If you see these features, then do this. But in machine learning, humans provide examples and let the machine figure out the rules itself. It's the difference between teaching someone to drive by giving them a detailed manual versus letting them practice and learn from their mistakes. The idea that machines could learn isn't new. In fact, it dates back to the 1950s, when scientists first began wondering if computers could be programmed to learn from experience. The British mathematician Alan Turing, in his 1950 paper Computing Machinery and Intelligence, asked a profound question: can machines think? He proposed what we now call the Turing test, suggesting that if a machine could converse in a way indistinguishable from a human, we might consider it intelligent. While Turing was thinking about general intelligence, his work laid important groundwork for thinking about machine learning. Around the same time, in 1956, a group of researchers organized what became known as the Dartmouth Conference. John McCarthy, a computer scientist at Dartmouth College, coined the term artificial intelligence for this event. Along with others like Marvin Minsky, Claude Shannon, and Herbert Simon, McCarthy envisioned creating machines that could learn and reason. Claude Shannon, known as the father of information theory, had already developed mathematical frameworks for understanding communication and data processing, which would prove essential for AI systems. One of the early pioneers of machine learning was Arthur Samuel, who in 1959 created a program that could play checkers. But here's what made it remarkable. Samuel didn't program it with all the best strategies. Instead, he let it play thousands of games against itself, and it learned which moves led to victory and which led to defeat. The program got better over time, eventually becoming good enough to beat its creator. This was revolutionary. It showed that machines could improve through experience, just like humans do. But the techniques were still quite limited. Early learning systems could only handle simple problems. They couldn't recognize images or understand language. They were like children learning to walk. Impressive, but still very basic. The breakthrough came with the development of neural networks, computer systems inspired by how our brains work. Our brains contain billions of neurons, cells that process information. These neurons are connected to each other in complex networks, and when we learn something new, the connections between neurons change. They get stronger or weaker, creating new pathways for information to flow. Artificial neural networks work in a similar way, though much simpler. They contain artificial neurons, simple processing units, that can receive inputs, do a calculation, and produce an output. These neurons are connected together in layers, and when the network learns, the strength of these connections changes. It's like adjusting the volume on different channels. Some connections become more important, others become less important, and gradually, the network gets better at its task. But we're getting ahead of ourselves. Before we dive into neural networks, let's think about what learning actually requires. For a machine to learn, it needs three things: data, a way to process that data, and feedback about whether it's doing well or poorly. Data is the raw material of learning. It's the examples, the experiences, the information that the machine uses to learn. For an image recognition system, the data might be thousands of photographs labeled with what they contain. For a language translation system, the data might be millions of sentences in 2 languages, showing how to translate between them. The more data, and the better the data, the more the machine can learn. But data alone isn't enough. The machine needs a way to process that data, to find patterns in it, to extract useful information. This is where algorithms come in. An algorithm is just a set of instructions, a recipe for how to process information. Learning algorithms are special because they can adjust themselves. They can change their behavior based on what they see in the data. Finally, the machine needs feedback. It needs to know when it's right and when it's wrong. This feedback allows it to adjust, to correct its mistakes, to gradually improve. In supervised learning, the most common type, this feedback comes in the form of labels. Each example comes with the correct answer. This is a picture of a cat. This sentence means, hello, in French. The machine makes a prediction, compares it to the correct answer, and adjusts if it was wrong. This process of making predictions, getting feedback, and adjusting is the heart of machine learning. It's iterative, meaning it happens over and over again. Each time through, the machine gets a little better. Each adjustment makes it slightly more accurate. And over thousands or millions of iterations, these small improvements add up to something remarkable, a system that can do things it was never explicitly programmed to do. The key insight is that learning happens through adjustment. The machine doesn't start knowing the right answer. It starts with guesses, often quite bad ones. But each time it makes a mistake, it adjusts slightly. It changes its internal parameters, the settings that determine how it processes information. And gradually, through this process of trial and error, it converges on the right behavior. This is similar to how we learn. When you first try to play a musical instrument, you make many mistakes. But each time you practice, you get a little better. Your brain adjusts the connections between neurons, strengthening the pathways that lead to correct actions, and weakening those that lead to mistakes. Machine learning works the same way, just with artificial neurons, instead of biological ones. But here's something important. The machine doesn't understand what it's learning in the way we do. When an AI system learns to recognize cats, it doesn't develop a concept of catness the way a human would. Instead, it learns patterns. It learns that certain combinations of pixels, certain arrangements of shapes and colors, tend to appear together in pictures labeled as cats. It's learning statistical patterns, not conceptual understanding. This distinction is crucial. Machines learn patterns, not meaning. They learn correlations, not causes. They learn what tends to go together, not why things go together. This is why AI systems can be incredibly good at some tasks, while being completely clueless about others. They're pattern-matching machines, not thinking machines. Yet this pattern-matching ability is incredibly powerful. By finding patterns in vast amounts of data, AI systems can discover relationships that humans might never notice. They can recognize subtle differences that escape our attention. They can process information at scales and speeds that are impossible for humans. The foundation of machine learning, then, is this simple but profound idea. Machines can improve through experience. They can learn from examples. They can adjust their behavior based on feedback. And through this process, they can discover patterns and relationships that enable them to perform tasks they were never explicitly programmed to do. As we continue our journey, We'll see how this simple idea gets implemented in increasingly sophisticated ways. We'll explore the structures that enable learning, the algorithms that make it possible, and the remarkable capabilities that emerge. But always remember, at its heart, machine learning is about finding patterns in data, making adjustments based on feedback, and gradually improving through experience. It's a process that's both beautifully simple and astonishingly complex. Simple in its basic idea, learn from examples. Complex in its implementation. The mathematics, the algorithms, the engineering that makes it all work. But don't worry if the details seem overwhelming. The concepts themselves are accessible, and understanding them will help you see the wonder in how machines learn. So as we drift deeper into this exploration, keep in mind that learning, whether in humans or machines, is fundamentally about adaptation. It's about changing in response to experience. It's about getting better through practice. And in the world of artificial intelligence, this simple principle has led to systems that can do things that seemed impossible just a few decades ago. The journey from simple pattern recognition to sophisticated AI systems has been remarkable. And it all starts with this foundation, the idea that machines can learn, can improve, can discover patterns and relationships through experience. It's an idea that has transformed technology, and it's an idea we'll explore together over the next 2 hours. Chapter 2: The Building Blocks, Neural Networks. Now that we understand the foundation of learning, let's explore the structures that make it possible. The most important of these is the neural network, a system inspired by how our brains work, but implemented in computer code. Neural networks are the engines that power most modern AI systems, from image recognition to language translation to game-playing programs. A neural network is, at its core, a collection of simple processing units called neurons, connected together in a way that allows them to process information collectively. Each neuron is quite simple on its own. It receives inputs, does a basic calculation, and produces an output. But when you connect thousands or millions of these simple neurons together, something remarkable emerges: the ability to recognize complex patterns, to make sophisticated decisions, to learn. The concept of artificial neurons dates back to 1958, when Frank Rosenblatt, a psychologist at Cornell University, created what he called the perceptron. This was a single-layer neural network that could learn to classify patterns. Rosenblatt was inspired by how biological neurons work, and he showed that a simple network of artificial neurons could learn from examples. The perceptron was limited. It could only solve certain types of problems, but it demonstrated the fundamental idea that machines could learn by adjusting connections between simple processing units. Rosenblatt's work was groundbreaking, though it would be decades before the full potential of neural networks would be realized. Think of it like this: a single musical note is simple, but when you combine many notes in the right way, you get a symphony. Similarly, a single neuron is simple. But when you combine many neurons in the right way, you get a system that can learn and recognize patterns. The name neural network comes from the fact that these systems are inspired by biological neural networks, the networks of neurons in our brains. But it's important to understand that artificial neural networks are simplified models. They capture some of the essential features of how biological neurons work, but they're much simpler. A biological neuron is incredibly complex, with thousands of different types of connections and intricate chemical processes. An artificial neuron is just a mathematical function, a simple calculation. But this simplicity is actually a strength. By simplifying, we can understand how the system works, we can build it, we can train it, we can improve it. And remarkably, even these simplified models can achieve impressive results. So what does a single neuron do? Imagine you're trying to decide whether to go outside. You might consider several factors. Is it sunny? Is it warm? Is it raining? Each of these factors influences your decision. A neuron works similarly. It receives multiple inputs, each with a certain weight or importance. Some inputs might be more important than others. The temperature might matter more than whether there are clouds in the sky. The neuron multiplies each input by its weight, adds them all together, and then applies what's called an activation function. This activation function determines whether the neuron fires, whether it produces a strong output or a weak one. It's like a threshold. If the combined weighted inputs exceed a certain level, the neuron produces a strong signal. If not, it produces a weak signal, or no signal at all. This might sound abstract, but it's actually quite intuitive. Think about recognizing a face. Your brain doesn't look at the entire face at once. Instead, different neurons respond to different features: edges, curves, contrasts. Some neurons might fire strongly when they detect an eye shape, others when they detect a nose shape. And when enough of these feature-detecting neurons fire together, your brain recognizes that it's seeing a face. Artificial neurons work the same way. In an image recognition network, different neurons learn to detect different features. Some might learn to detect edges, others might learn to detect textures, still others might learn to detect more complex shapes. And when information flows through the network, from layer to layer, these simple features combine to form more complex recognitions. This brings us to one of the most important concepts in neural networks: layers. Neurons in a neural network are organized into layers, like floors in a building. Information flows from one layer to the next, getting processed and transformed along the way. The first layer is called the input layer. This is where information enters the network. If you're recognizing images, the input layer receives the pixel values. If you're processing text, the input layer receives the words or characters. The input layer doesn't do much processing, it just receives the raw data and passes it along. Then come the hidden layers. These are called hidden because they're between the input and output, not directly visible from the outside. Hidden layers are where the real work happens. They process the information, extract features, combine patterns. A network might have just one hidden layer, or it might have dozens, or even hundreds of them. The more layers, the more complex patterns the network can learn. Finally, there's the output layer. This produces the final result, the network's answer to whatever question it's trying to answer. If the network is recognizing images, the output layer might have neurons for different categories. One neuron for cat, another for dog, another for bird. The neuron with the strongest output indicates the network's prediction. The connections between neurons are crucial. Each connection has a weight, a number that determines how strongly the signal from one neuron influences the next. These weights are what the network learns during training. Initially, the weights are set to random values. The network doesn't know anything yet. But as it sees examples and gets feedback, it adjusts these weights. Connections that lead to correct answers get stronger. Connections that lead to mistakes get weaker. This is the essence of learning in a neural network, adjusting the weights of connections. It's like tuning a radio. At first you might get static, but as you adjust the dial, you find the right frequency, and suddenly you hear music clearly. Similarly, a neural network starts with random weights, producing random outputs. But as it adjusts the weights through training, it finds the right settings, and suddenly, it can recognize patterns accurately. The process of information flowing through the network is called a forward pass. You feed in an input, and the information flows forward, layer by layer, with each layer processing and transforming it. By the time it reaches the output layer, the information has been transformed from raw data into a prediction. But here's what makes neural networks powerful. They can learn to extract features automatically. You don't have to tell the network what features to look for. You don't have to program it to detect edges or shapes or textures. Instead, through training, the network discovers these features on its own. The early layers might learn to detect simple features like edges. The middle layers might learn to detect more complex features like shapes or textures. And the later layers might learn to detect very complex features like objects or scenes. This ability to automatically discover features is one of the key advantages of neural networks. Traditional computer vision systems required humans to hand-design features. Engineers had to figure out what made a cat look like a cat, program those features explicitly, and hope they worked. But neural networks can discover features that humans might never think of, features that are optimal for the specific task at hand. The complexity that emerges from simple components is one of the most beautiful aspects of neural networks. Each neuron is simple, each connection is simple. But when you combine thousands or millions of them in the right way, you get a system that can recognize faces, translate languages, play games, and do countless other tasks. This emergence of complexity from simplicity is a theme that appears throughout nature. A single water molecule is simple, but billions of them create the complex behavior of oceans and weather. A single ant is simple, but a colony of ants creates complex social structures. Similarly, a single neuron is simple, but a network of neurons creates the ability to learn and recognize patterns. This idea that intelligence emerges from the interaction of simple components was explored by Marvin Minsky, a co-founder of MIT's AI laboratory. In his book, The Society of Mind, published in 1985, Minsky proposed that intelligence arises from the interaction of many non-intelligent parts. Just as a society emerges from the interactions of individual people, each with limited capabilities, intelligence might emerge from the interactions of simple processing units, each performing basic operations. Minsky's work helped shape how researchers think about building intelligent systems from simple components, an idea that resonates strongly with how neural networks work. The structure of a neural network matters enormously. How many layers should it have? How many neurons in each layer? How should they be connected? These are questions that researchers are still exploring. Different architectures work better for different tasks. A network designed for image recognition might have a different structure than one designed for language processing. But regardless of the specific architecture, the fundamental principle remains the same. Simple processing units, connected together, processing information layer by layer, with the ability to adjust their connections through learning. It's a simple idea, but it's the foundation of modern artificial intelligence. As we continue our exploration, we'll see how these networks actually learn. We'll discover how they adjust their weights, how they improve through experience, and how they discover patterns in data. But always remember, at its heart, a neural network is just a collection of simple processing units, connected together, working collectively to recognize patterns and make predictions. The beauty is in the simplicity. Each component is understandable, each step is clear. But together they create something remarkable, a system that can learn, that can improve, that can discover patterns and relationships, that enable it to perform tasks it was never explicitly programmed to do. Chapter 3: The Learning Process, Training. Now that we understand the structure of neural networks, let's explore how they actually learn. This process is called training, and it's where the magic happens. Training is when a neural network sees examples, makes predictions, gets feedback, and gradually improves. It's the process that transforms a network with random weights into a system that can recognize patterns accurately. Imagine you're teaching someone to recognize different types of birds. You might show them many examples, this is a robin, this is a sparrow, this is an eagle. Each time they see an example, they learn a little bit more about what makes each bird distinctive. After seeing hundreds or thousands of examples, they become quite good at recognizing birds, even ones they've never seen before. Training a neural network works similarly. You show it many examples, each labeled with the correct answer. The network makes a prediction, compares it to the correct answer, and adjusts if it was wrong. Over time, through thousands or millions of examples, the network gets better and better. But let's break this down step by step. The first thing you need for training is a dataset, a collection of examples. If you're training an image recognition system, your dataset might contain thousands of photographs, each labeled with what it shows. This is a cat, this is a dog, this is a car. The quality and quantity of this data is crucial. More data usually means better learning, and better data means more accurate results. The dataset is typically divided into 3 parts: a training set, a validation set, and a test set. The training set is what the network uses to learn. It's like the practice problems you work through when learning a new skill. The validation set is used to check how well the network is learning, to tune its settings, to make sure it's not just memorizing the training examples. And the test set is used at the very end, to see how well the network performs on completely new examples it has never seen before. This division is important because we want the network to generalize to work well on new examples, not just on the ones it was trained on. It's the difference between memorizing answers to specific questions and actually understanding the concepts. A student who memorizes answers might do well on the exact questions they studied, but poorly on new questions. Similarly, a network that just memorizes its training examples won't work well on new images. We want it to learn the underlying patterns, not just memorize specific cases. Once you have your dataset, training begins. The process starts with initialization. All the weights in the network are set to small random values. The network doesn't know anything yet. It's like a newborn baby, ready to learn, but starting from zero knowledge. Then comes the training loop, which repeats many times. Each repetition is called an epoch, and an epoch typically involves showing the network all the examples in the training set once. But the network doesn't process all examples at once. Instead, it processes them in small groups called batches. A batch might contain 32 examples, or 64, or 128. Processing in batches makes training more efficient and stable. For each example in a batch, the network performs what's called a forward pass. The input data flows through the network, layer by layer. Each layer processes the information, applying weights and activation functions. By the time the information reaches the output layer, the network has made a prediction. Let's say you're training a network to recognize handwritten digits, 0 through 9. You show it an image of the number 7. The image, represented as pixel values, enters the input layer. It flows through the hidden layers, getting processed and transformed. Finally, it reaches the output layer, which has 10 neurons, one for each digit. Each neuron produces a value, indicating how confident the network is that the input is that digit. The neuron for 7 might produce a value of 0.8, while the neuron for 3 might produce 0.1. But initially, before training, these predictions are essentially random. The network might think a 7 is a 3 or a 2 or any digit with roughly equal probability. It doesn't know anything yet. This is where the learning happens. The network compares its prediction to the correct answer. If it predicted 3 but the correct answer is 7, it knows it made a mistake. It calculates an error, a measure, of how wrong it was. This error is then used to adjust the weights throughout the network, making it slightly more likely to get the right answer next time. The process of calculating the error and using it to adjust weights is called backpropagation, and we'll explore it in detail in the next chapter. But the basic idea is simple. The network figures out which connections contributed to the mistake, and it adjusts them. Connections that led to the wrong answer get weakened. Connections that would have led to the right answer get strengthened. This adjustment happens for every example in the batch. After processing a batch, the network has made many predictions, calculated many errors, and made many small adjustments. Then it moves on to the next batch, and the process repeats. After processing all batches in the training set, one epoch is complete. The network has seen all the training examples once, made predictions for all of them, and adjusted its weights many times. But one epoch is usually not enough. The network needs to see the examples many times, often hundreds or thousands of epochs, before it learns well. This might seem inefficient. Why does the network need to see the same examples over and over? The answer is that learning happens gradually. Each time through, the network makes small adjustments. It doesn't jump from random guesses to perfect accuracy in one go. Instead, it gradually converges on the right behavior, getting a little better with each epoch. Think of it like learning to play a musical instrument. You don't play a piece perfectly the first time you try it. You practice it many times, making small improvements each time. After dozens or hundreds of repetitions, you can play it well. Similarly, a neural network needs many epochs to learn well. The number of epochs needed depends on many factors: the complexity of the task, the size of the network, the quality of the data, and more. Simple tasks might need just a few epochs. Complex tasks might need thousands. Researchers monitor the network's performance during training, watching to see when it stops improving, when it has learned as much as it can from the data. But there's a danger here: overfitting. This happens when the network learns the training examples too well. It memorizes them, including their quirks and noise, rather than learning the underlying patterns. A network that overfits might perform perfectly on the training examples, but poorly on new examples. It's like a student who memorizes answers without understanding the concepts. To prevent overfitting, researchers use various techniques. They might stop training early, before the network starts memorizing. They might add regularization, techniques that encourage the network to learn simpler patterns. Or they might use dropout, randomly disabling some neurons during training, which forces the network to be more robust. The training process is computationally intensive. Modern neural networks might have millions, or even billions of weights to adjust. Processing millions of examples, running thousands of epochs, can take days or weeks, even on powerful computers. This is why training often happens on specialized hardware like graphics processing units, or GPUs, which can perform many calculations in parallel. But despite the computational complexity, the fundamental process is simple: show examples, make predictions, calculate errors, adjust weights, repeat. It's an iterative process, where small improvements accumulate over time into something remarkable. The beauty of this process is that it's automatic. Once you set up the network architecture and provide the data, the learning happens on its own. You don't have to figure out what features to detect, or what rules to follow. The network discovers these through training. This is what makes machine learning so powerful. It can discover patterns that humans might never notice. It can find relationships in data that are too complex for explicit programming. And it can adapt to new types of data, learning to recognize patterns it has never seen before. As training progresses, you can watch the network improve. Initially, its predictions are random, but gradually it starts getting some answers right, then more and more. Eventually, it might achieve accuracy of 90%, or 95%, or even higher, depending on the task. But training never makes a network perfect. There's always some error. Some cases it gets wrong. This is because the patterns in real-world data are never perfectly clear. There's always noise, always exceptions, always edge cases. The goal isn't perfection, but good enough performance for the task at hand. The training process is complete when the network stops improving, or when it reaches a satisfactory level of performance. At that point, the weights are frozen. The network is ready to be used. It can now make predictions on new examples, using what it learned during training. This is the difference between training and inference. Training is the learning phase, where the network adjusts its weights. Inference is the using phase, where the network makes predictions with fixed weights. Once training is complete, the network can be deployed, used in applications, making predictions on new data it has never seen before. The entire process, from random initialization to a trained network, is remarkable. It shows how simple rules, applied repeatedly, can lead to complex behavior. It demonstrates how learning can emerge from the right combination of structure, data, and feedback. And it reveals how machines can discover patterns and relationships that enable them to perform tasks they were never explicitly programmed to do. As we continue our exploration, we'll dive deeper into how the network actually adjusts its weights, how backpropagation works, and how errors flow backward through the network to enable learning. But always remember, at its heart, training is about showing examples, making predictions, getting feedback, and gradually improving. It's a process that's both beautifully simple and astonishingly powerful. Chapter 4: Learning from Mistakes, the Magic of Backpropagation. We've seen how neural networks make predictions during training, and we've mentioned that they adjust their weights when they make mistakes. But how exactly does this adjustment happen? How does the network know which weights to change, and by how much? The answer lies in one of the most elegant algorithms in computer science: backpropagation. Backpropagation, short for backward propagation of errors, is the algorithm that allows neural networks to learn from their mistakes. It's the mechanism that takes an error at the output and figures out how to adjust all the weights throughout the network to reduce that error. Without backpropagation, neural networks couldn't learn. It's that fundamental. The modern form of backpropagation was developed in the 1980s by researchers including Geoffrey Hinton, David Rumelhart, and Ronald Williams. In 1986, Rumelhart, Hinton, and Williams published a paper that showed how backpropagation could train multi-layer neural networks effectively. Geoffrey Hinton, often called the godfather of deep learning, has spent decades advancing neural network research, even during periods when the field was out of favor. His persistence and insights into how networks learn have been instrumental in the modern AI revolution. Hinton's work on backpropagation and deep learning eventually led to breakthroughs that transformed the field, including the 2012 ImageNet competition, where deep neural networks dramatically outperformed traditional computer vision methods. The name backpropagation comes from the fact that errors flow backward through the network, from the output layer back to the input layer. Information flows forward during prediction, but errors flow backward during learning. It's like retracing your steps when you realize you took a wrong turn. You go back along the path you took, figuring out where you went wrong and how to correct it. Let's think about this with a simple analogy. Imagine you're learning to throw a ball at a target. You throw it, and it lands too far to the right. You know you made a mistake, but how do you correct it? You need to figure out what you did wrong. Was it the angle of your arm, the timing of your release, the force you applied? And you need to adjust these things for your next throw. A neural network faces a similar challenge, but much more complex. When it makes a wrong prediction, it knows it's wrong, but it needs to figure out which of its millions of weights contributed to the mistake, and how to adjust them. Backpropagation solves this problem. The key insight is the chain rule from calculus. Without getting too deep into mathematics, The chain rule allows you to figure out how a small change in one variable affects the final result, even when there are many intermediate steps. In a neural network, a change in a weight in an early layer affects the output through many intermediate layers. The chain rule lets us trace this effect backward, figuring out how much each weight contributed to the error. Here's how it works in practice. During a forward pass, the network makes a prediction. Let's say it's trying to recognize a handwritten 7, but it predicts 3 instead. The network calculates an error, a measure of how wrong it was. This error is larger for the 3 neuron, which incorrectly fired strongly, and smaller for other neurons. Now comes the backward pass. The network starts at the output layer and works backward. For each neuron in the output layer, it calculates how much that neuron's output contributed to the error. If the 3 neuron fired too strongly, it needs to be reduced. If the 7 neuron didn't fire strongly enough, it needs to be increased. But here's the crucial part. The network doesn't just adjust the output layer. It figures out how much each neuron in the previous layer contributed to the error. It does this by looking at the connections. If a neuron in a hidden layer was strongly connected to the 3 neuron that fired incorrectly, that hidden neuron probably contributed to the mistake. Its connections need to be adjusted. This process continues layer by layer, all the way back to the input layer. For each neuron, the network calculates how much it contributed to the error. For each connection, it calculates how much adjusting that connection would reduce the error. And then it makes small adjustments to all the weights, proportional to how much they contributed to the mistake. The size of these adjustments is controlled by something called the learning rate. This is a crucial parameter in training. If the learning rate is too high, the network makes big adjustments, and it might overshoot, jumping past the right answer. It's like adjusting a radio dial too quickly. You might skip right past the station you're trying to find. If the learning rate is too low, the network makes tiny adjustments, and learning is very slow. It might take forever to converge on good weights. It's like trying to fill a bathtub with a dripping faucet. It works, but it takes a very long time. The right learning rate is somewhere in between, large enough that learning happens in a reasonable time, but small enough that the network can converge smoothly on good weights. Finding the right learning rate is often a matter of trial and error, though there are techniques that can help. The adjustments made during backpropagation are typically very small. A weight might change by 0.001 or 0.0001, or even smaller. But these tiny changes accumulate. Over thousands or millions of examples over many epochs, these small adjustments add up to significant changes. The network gradually shifts from random weights to weights that enable accurate predictions. This is similar to how we learn physical skills. When you first try to ride a bike, you make many mistakes. But each time you fall, you make small adjustments. You shift your weight slightly. You adjust your balance. You change how you pedal. Individually, these adjustments are tiny. But over many attempts they accumulate, and eventually you can ride smoothly. Backpropagation enables this same kind of gradual improvement in neural networks. Each mistake leads to small adjustments. Each adjustment makes the network slightly better. And over time these improvements accumulate into accurate performance. But backpropagation isn't perfect. It has limitations. One limitation is that it can get stuck in local minima. Imagine you're trying to find the lowest point in a landscape, with many hills and valleys. You might find a valley that's lower than the surrounding area, but not the lowest valley overall. You're stuck in a local minimum, unable to find the global minimum. Similarly, during training, the network might find weights that work reasonably well, but not the best possible weights. The error might be low, but not as low as it could be. This is why training often involves multiple attempts, starting from different random initializations, hoping to find better solutions. Another limitation is that backpropagation requires the network to be differentiable. This is a mathematical requirement that means the functions used in the network must be smooth enough that we can calculate how small changes affect the output. This is why activation functions in neural networks are chosen carefully. They need to be differentiable while still providing the nonlinearity that makes neural networks powerful. Despite these limitations, backpropagation is remarkably effective. It's the algorithm that enabled the modern era of deep learning. Without it, training deep neural networks would be essentially impossible. With it, we can train networks with dozens or hundreds of layers, networks with billions of parameters, networks that can perform tasks that seemed impossible just a few decades ago. The elegance of backpropagation lies in its simplicity. The basic idea is straightforward, errors flow backward, and weights are adjusted proportionally. But this simple idea, when applied to complex networks, enables learning of remarkable sophistication. As you drift deeper into this exploration, think about how remarkable this process is. A network starts with random weights, knowing nothing. Through backpropagation, it learns from its mistakes, adjusting millions of parameters, gradually converging on weights that enable accurate predictions. It's a process that's automatic, that requires no human intervention once it's set up, and that can discover patterns humans might never notice. The magic isn't in any single step of backpropagation. Each step is just a calculation, just mathematics. The magic is in how these simple calculations, repeated millions of times, enable learning. It's emergence again. Simple rules creating complex behavior. Basic mathematics enabling sophisticated capabilities. Backpropagation is the engine of learning in neural networks. It's what transforms random weights into useful patterns. It's what enables machines to learn from examples, to improve through experience, to discover relationships in data. And understanding how it works helps us appreciate the remarkable process that powers modern artificial intelligence. Chapter 5: Different Ways to Learn. So far we've been talking about supervised learning, where the network learns from labeled examples. You show it a picture labeled cat, and it learns to recognize cats. You show it a sentence with its translation, and it learns to translate. But supervised learning is just one way that machines can learn. There are other approaches, each suited to different types of problems, each with its own strengths and challenges. Let's explore these different learning paradigms. Understanding them will help us appreciate the diversity of approaches in artificial intelligence, and see how different problems require different solutions. Supervised learning is like learning with a teacher. Every example comes with a label, with the correct answer. This is a cat. This sentence means hello, in French. This email is spam. The network learns by comparing its predictions to these correct answers, adjusting when it's wrong. It's the most common type of machine learning, used for tasks like image recognition, language translation, spam detection, and medical diagnosis. The strength of supervised learning is that it's straightforward. You have clear examples with clear answers, and the network learns to map inputs to outputs. But it requires labeled data, which can be expensive and time-consuming to create. Someone has to go through thousands or millions of examples and label them correctly. For some tasks, this is feasible. For others, it's not. This brings us to unsupervised learning, where the network learns from data without labels. There's no teacher, no correct answers provided. Instead, the network tries to find patterns in the data on its own. It's like exploring a new city without a map. You don't know where things are, but you can still discover interesting neighborhoods and connections. One common task in unsupervised learning is clustering, grouping similar examples together. Imagine you have a collection of customer data, ages, incomes, purchase histories. Without labels, you can't tell the network, these are young professionals, or these are retirees. But through unsupervised learning, the network might discover that the data naturally forms clusters, groups of similar customers. It might find patterns you didn't know existed. Another task is dimensionality reduction, finding simpler representations of complex data. You might have data with hundreds of features, but many of them might be redundant or less important. Unsupervised learning can discover which features matter most, creating a simpler representation that captures the essential information. Unsupervised learning is powerful because it doesn't require labels. You can learn from vast amounts of unlabeled data, which is often easier to obtain. But it's also more challenging. Without correct answers to compare against, it's harder to know if the network is learning useful patterns or just finding noise. The patterns it discovers might be interesting, but are they meaningful? That's often a matter of interpretation. Then there's reinforcement learning, which is like learning through trial and error with rewards and punishments. The network doesn't learn from labeled examples. Instead, it interacts with an environment, takes actions, and receives feedback in the form of rewards or penalties. It learns which actions lead to good outcomes and which lead to bad ones. Think about learning to play a video game. You don't have a teacher telling you the right move for every situation. Instead, you try different actions, see what happens, and learn from the results. If you score points, that's good. If you lose a life, that's bad. Over time, you learn strategies that maximize your score. Reinforcement learning works similarly. The network takes actions in an environment, receives rewards or penalties, and learns to maximize rewards over time. It's being used to train AI systems that can play games like chess and Go at superhuman levels, that can control robots, that can optimize complex systems. The foundations of reinforcement learning were laid by researchers like Richard Bellman, who developed dynamic programming in the 1950s, and later by Andrew Bartow and Richard Sutton, who helped establish reinforcement learning as a distinct field of machine learning. Their work showed how agents could learn optimal behaviors through trial and error, receiving feedback in the form of rewards or penalties. The challenge with reinforcement learning is that feedback is often sparse and delayed. In a game, you might take many actions before you win or lose. Which actions contributed to the outcome? It's not always clear. The network has to figure out which actions were important, which is a complex credit assignment problem. But reinforcement learning is powerful because it can learn complex behaviors through interaction. It doesn't need examples of perfect play. It can discover strategies through exploration, sometimes finding approaches that humans never considered. There's also transfer learning, where a network trained on one task is adapted for a different but related task. It's like a musician learning a new instrument. They don't start from scratch. Their knowledge of music theory, rhythm, and melody transfers over, making learning the new instrument easier. In transfer learning, a network might be trained on a large dataset for a general task, like recognizing objects in images. Then, with relatively little additional training, it can be adapted for a specific task, like recognizing medical conditions in X-rays. The early layers, which learn to detect basic features like edges and shapes, are useful for both tasks. Only the later layers need to be retrained for the specific application. Transfer learning is powerful because it allows networks to leverage knowledge from large datasets, even when you only have a small dataset for your specific task. It's made it possible to apply deep learning to domains where collecting large labeled datasets would be impractical. These different learning paradigms aren't mutually exclusive. Modern AI systems often combine them. A system might use unsupervised learning to discover features, supervised learning to recognize patterns, and reinforcement learning to optimize behavior. The choice of approach depends on the problem, the available data, and the desired outcome. Each paradigm has its place. Supervised learning excels when you have labeled data and clear objectives. Unsupervised learning shines when you want to explore data and discover unknown patterns. Reinforcement learning is ideal when you can interact with an environment and learn through trial and error. And transfer learning helps when you have limited data, but can leverage knowledge from related tasks. Understanding these different approaches helps us appreciate the diversity of machine learning. There's no one-size-fits-all solution. Different problems require different approaches, and the art of machine learning lies in choosing the right approach for the task at hand. As we continue our exploration, we'll see how these different learning paradigms enable different capabilities. We'll discover how supervised learning powers image recognition, how unsupervised learning discovers hidden patterns, how reinforcement learning enables game-playing AI, and how transfer learning makes it possible to apply AI to new domains with limited data. But always remember, regardless of the paradigm, the fundamental process remains the same. Machines learn by processing data, finding patterns, making predictions, getting feedback, and adjusting. The details vary, but the essence is consistent: learning through experience, improvement through iteration, discovery through exploration. Chapter 6: What AI actually learns. We've explored how neural networks learn, but what exactly do they learn? When a network trains on thousands of cat images, what does it actually discover? What knowledge does it acquire? Understanding what AI learns helps us appreciate both its capabilities and its limitations. At the most basic level, a neural network learns weights. These are just numbers, values that determine how strongly neurons influence each other. But these numbers encode something remarkable: patterns. The network discovers which combinations of features tend to appear together, which patterns are associated with which outcomes, which relationships exist in the data. When a network learns to recognize cats, it doesn't learn a definition of cat the way a human would. It doesn't develop a concept like, a cat is a small carnivorous mammal with whiskers and a tail. Instead, it learns statistical patterns. It learns that certain combinations of pixels, certain arrangements of shapes and colors, certain textures and edges, tend to appear together in images labeled as cats. These patterns are what researchers call features. Features are the building blocks that the network learns to detect. In early layers, features might be simple: edges, curves, corners. In middle layers, features become more complex: shapes, textures, parts of objects. In later layers, features might be very complex: entire objects, scenes, or concepts. The network learns these features automatically, without being told what to look for. Through training, it discovers which features are useful for the task. Features that help distinguish cats from dogs get strengthened. Features that don't help get weakened or ignored. This automatic feature discovery is one of the key advantages of neural networks. Traditional computer vision systems required humans to hand-design features. Engineers had to figure out what made a cat look like a cat, program those features explicitly, and hope they worked. But neural networks can discover features that humans might never think of, features that are optimal for the specific task. But here's something important. The network learns patterns, not rules. It learns what tends to happen, not why it happens. It learns correlations, not causes. This is a crucial distinction. A network might learn that images with certain features are usually cats, but it doesn't understand why. It doesn't have a model of what a cat is, what cats do, why cats look the way they do. This is why AI systems can be incredibly good at some tasks, while being completely clueless about others. They're excellent at pattern recognition, at finding statistical relationships in data. But they struggle with reasoning, with understanding cause and effect, with generalizing beyond their training data, in ways that require true understanding. The network also learns representations, ways of organizing information. As data flows through the network, it gets transformed. Raw pixel values become edges, edges become shapes, shapes become objects. Each layer creates a new representation, a new way of looking at the information. These representations become increasingly abstract, moving from low-level details to high-level concepts. These representations are learned, not programmed. The network discovers how to organize information in ways that are useful for the task. Different networks might learn different representations for the same data, depending on what they're trying to accomplish. A network trained to recognize objects might learn different representations than one trained to recognize emotions in faces. But there's a difference between learning patterns and understanding them. A network might learn that certain patterns are associated with certain labels, but it doesn't understand what those patterns mean. It's like learning to recognize a word in a foreign language by its shape, without understanding what the word means. You can identify it correctly, but you don't truly understand it. This distinction between pattern recognition and true understanding was explored by the philosopher John Searle in a famous thought experiment he called the Chinese room. Imagine you're locked in a room with a huge book of rules written in English. Through a slot in the door, someone slides in pieces of paper with Chinese characters written on them. You don't understand Chinese at all, but you follow the rules in the book. The rules tell you which Chinese characters to write down in response. Based on which characters you received, you write down the response and slide it back out. To someone outside the room, it appears that you understand Chinese. They write questions in Chinese, and you respond appropriately. But you don't understand Chinese at all. You're just following rules, manipulating symbols according to instructions, without any comprehension of what those symbols mean. Searle argued that this is what computers do when they process language. They manipulate symbols according to rules, but they don't understand the meaning of those symbols. They can produce correct outputs, but they lack true understanding. This thought experiment, first presented in 1980, raises profound questions about what it means to understand, and whether machines can ever truly understand language, or just simulate understanding through pattern matching. The Chinese room argument has been debated by philosophers and AI researchers for decades. Some argue that understanding emerges from the system as a whole, not from individual components. Others point out that understanding might be more about behavior than internal states. But Searle's point remains relevant. There's a difference between producing correct outputs and truly understanding what you're doing. This distinction helps us appreciate both the remarkable capabilities of AI systems and their fundamental limitations. This is why AI systems can sometimes surprise us. They might recognize patterns we didn't notice, find relationships we didn't see, but they might also make mistakes that seem obvious to us, fail in ways that reveal their lack of true understanding. They're pattern-matching machines, incredibly sophisticated ones, but pattern-matching machines nonetheless. The network also learns to generalize, to apply what it learned from training examples to new examples it has never seen. This is crucial. If a network could only recognize the exact images it was trained on, it would be useless. Instead, it learns to recognize the underlying patterns, which allows it to work on new images. But generalization has limits. A network trained on photos of cats might work well on new photos, but it might fail on drawings of cats, or cats in unusual poses, or cats of breeds it hasn't seen. It generalizes within the distribution of its training data, but struggles outside that distribution. This is why the quality and diversity of training data matters so much. A network trained on limited, biased data will learn limited, biased patterns. It will generalize poorly, failing on examples that differ from what it saw during training. This is one of the key challenges in machine learning, ensuring that training data is representative of the real-world situations where the system will be used. The network also learns what to ignore, what features are noise rather than signal. In any dataset, there's variation that matters, and variation that doesn't. A network learning to recognize faces needs to pay attention to facial features, but it can ignore background details, lighting conditions, camera angles. Through training, it learns which variations are important and which can be ignored. This ability to focus on what matters is crucial. Real-world data is messy. There's always noise, always irrelevant variation. A network that learned to pay attention to everything would be overwhelmed. Instead, it learns to extract the signal from the noise, to focus on features that help with the task, and ignore features that don't. But this also means that networks can learn the wrong things. If training data has biases, the network will learn those biases. If certain patterns are correlated with certain outcomes in the training data, for reasons that won't hold in the real world, the network will learn those correlations anyway. It doesn't understand causality, so it can't distinguish between meaningful correlations and spurious ones. This limitation was highlighted by Judea Pearl, a computer scientist who won the Turing Award for his work on probabilistic reasoning and causal inference. Pearl developed Bayesian networks, which can represent and reason about uncertainty, and he emphasized the importance of understanding causality in AI systems. Traditional machine learning excels at finding correlations, patterns that occur together, but struggles with understanding cause and effect. Pearl's work has been influential in developing AI systems that can reason about why things happen, not just what tends to happen together. His framework for causal reasoning helps us understand the difference between this is associated with that, and this causes that, a distinction that's crucial for building AI systems that can truly understand the world. This is why testing and validation are so important. A network might perform perfectly on training data, but fail on new data if it learned patterns that don't generalize. Or it might learn patterns that work, but for the wrong reasons. Patterns that will break when conditions change. What AI learns, then, is complex. It learns weights that encode patterns. It learns features that are useful for the task. It learns representations that organize information effectively. It learns to generalize within certain limits. It learns what to pay attention to and what to ignore. But it doesn't learn understanding in the human sense. It doesn't learn concepts, causes, or meanings. It learns statistical patterns, correlations, associations. This is both its strength and its limitation. It enables remarkable capabilities, but it also means that AI systems work differently than human intelligence, with different strengths and different weaknesses. As we continue our exploration, we'll see how these learned patterns enable real-world applications, from image recognition to language understanding. We'll discover what AI can do with what it learns, and what it struggles with, but always remember, AI learns patterns, not understanding. It's a crucial distinction that helps us appreciate both the power and the limits of artificial intelligence. Chapter 7: The Challenges of Learning. Learning isn't always smooth or straightforward, whether for humans or machines. Neural networks face many challenges as they learn, and understanding these challenges helps us appreciate both the difficulty of creating effective AI systems and the techniques researchers use to overcome obstacles. One of the most common problems is overfitting. This happens when a network learns its training examples too well. It memorizes them, including their quirks and noise, rather than learning the underlying patterns that generalize to new examples. It's like a student who memorizes answers to specific questions, without understanding the concepts. They might ace the practice test, but fail on new questions. Overfitting is easy to spot. The network performs excellently on training data, but poorly on new data. It's learned the training set, but it hasn't learned to generalize. This is a fundamental challenge in machine learning. How do you ensure that a network learns useful patterns, rather than just memorizing examples? Researchers use several techniques to prevent overfitting. One is early stopping. You monitor the network's performance on validation data during training, and stop when it stops improving. This prevents the network from continuing to memorize training examples after it has learned the useful patterns. Another technique is regularization, which encourages the network to learn simpler patterns. Simpler patterns tend to generalize better. A network that learns cats have 4 legs, fur, and pointy ears will work better on new cats than one that memorizes specific pixel patterns from training images. Regularization techniques add penalties for complexity, encouraging the network to find simpler solutions. Dropout is another powerful technique. During training, some neurons are randomly disabled, turned off temporarily. This forces the network to be more robust, to not rely too heavily on any single neuron or pathway. It's like practicing a skill with one hand tied behind your back. It forces you to develop more flexible approaches. But overfitting isn't the only challenge. There's also underfitting, when a network doesn't learn enough. It might be too simple, with too few neurons or layers to capture the patterns in the data. Or it might not train long enough, stopping before it has learned the useful patterns. An underfit network performs poorly on both training and new data. It hasn't learned the task at all. Finding the right balance between overfitting and underfitting is one of the key challenges in machine learning. You want a network that's complex enough to learn the patterns, but not so complex that it memorizes noise. You want it to train long enough to learn well, but not so long that it starts memorizing. The quality and quantity of data also present challenges. A network can only learn patterns that exist in its training data. If the data is limited, the network's knowledge will be limited. If the data is biased, the network will learn those biases. If the data doesn't represent the real-world situations where the system will be used, the network will struggle. This is why collecting good training data is so important and so challenging. You need enough data, diverse data, representative data. For some tasks this is feasible. For others it's extremely difficult. How do you collect enough examples of rare medical conditions? How do you ensure your data represents all the people who will use your system? These are ongoing challenges. The importance of large, diverse datasets was demonstrated by Fei-Fei Li, a computer scientist at Stanford University. In 2009, Li and her colleagues created ImageNet, a dataset containing millions of labeled images across thousands of categories. This massive dataset enabled researchers to train deep neural networks effectively, leading to breakthroughs in image recognition. Li's work showed that having the right data, lots of it, well organized and diverse, was just as important as having good algorithms. Her emphasis on the importance of data quality and diversity has influenced how researchers think about training AI systems. Li has also been a vocal advocate for ethical AI development and diversity in the field, co-founding AI4ALL, to promote inclusivity in AI research. Bias in training data is a particularly serious problem. If your training data contains biases, the network will learn those biases. If your face recognition system is trained mostly on images of people with certain skin tones, it will perform poorly on people with other skin tones. If your language model is trained on text that contains gender stereotypes, it will reproduce those stereotypes. This isn't a technical problem that can be solved with better algorithms. It's a fundamental issue with how the data is collected and what it represents. Addressing bias requires careful attention to data collection, to ensuring that training data is representative and fair. It's an ongoing challenge that researchers and practitioners are actively working to address. Another challenge is the need for testing and validation. How do you know if a network has learned well? You can't just test it on the data it was trained on. That would be like giving a student the same test they studied from. You need separate test data, data the network has never seen, to evaluate its true performance. But even test data can be misleading if it's not truly representative. A network might perform well on test data, but fail in real-world use, if the test data doesn't capture the diversity and challenges of actual deployment. This is why real-world testing is so important, why systems need to be monitored and evaluated continuously after deployment. Computational challenges are also significant. Training large neural networks requires enormous computational resources. Networks with billions of parameters might need weeks or months of training on specialized hardware. This limits who can train large models, and it has environmental costs as well. The energy required for training large AI systems is substantial. There are also challenges related to interpretability. When a network makes a prediction, how do you know why? Which features did it use? Which patterns did it recognize? For some applications, this doesn't matter. But for others, like medical diagnosis or loan approval, understanding why the system made a decision is crucial. Yet neural networks are often black boxes, making it difficult to understand their reasoning. Researchers are working on techniques to make neural networks more interpretable, to understand what they've learned and why they make certain predictions. But this remains an active area of research, with no perfect solutions yet. This challenge is part of a broader concern about AI safety and alignment, ensuring that AI systems behave in ways that are beneficial to humans. Stuart Russell, a computer scientist at UC Berkeley and co-author of the widely used textbook Artificial Intelligence: A Modern Approach, has been a leading voice in advocating for AI safety research. Russell emphasizes that as AI systems become more powerful, we need to ensure they're aligned with human values, and that we can understand and control their behavior. His work highlights the importance of developing AI systems that are not just capable, but also safe, interpretable and beneficial. Despite these challenges, neural networks have achieved remarkable success. The techniques for addressing overfitting, the methods for collecting and preparing data, the approaches to testing and validation, have all improved over time. But the challenges remain, and they remind us that creating effective AI systems is difficult, requiring careful attention to many factors. As we continue our exploration, we'll see how these challenges are addressed in real-world applications. We'll discover how researchers and practitioners work to create systems that learn well, generalize effectively, and perform reliably. But always remember, learning is hard, whether for humans or machines. The challenges are real, but so are the techniques for overcoming them. The fact that neural networks can learn at all, despite these challenges, is remarkable. That they can learn patterns, recognize images, understand language, play games, and perform countless other tasks, is a testament to both the power of the approach and the ingenuity of the researchers who have developed techniques to overcome obstacles. Learning is a journey, not a destination. Networks don't learn perfectly. They make mistakes, they face challenges, but through careful design, good data, effective training, and continuous improvement, they can learn to perform tasks that seemed impossible just a few decades ago. Chapter 9: The Future of Learning. As we near the end of our exploration, it's natural to wonder, where is machine learning heading? What are the current limitations, and how might they be overcome? What new techniques are researchers developing? What might be possible in the years and decades to come? The field of machine learning is moving incredibly fast. New papers are published daily, new techniques emerge regularly, new capabilities are demonstrated constantly. It's an exciting time, but also a time of uncertainty. Predicting the future of technology is always difficult, and AI is no exception. But we can look at current trends, ongoing research, and emerging directions to get a sense of where things might be heading. One of the most active areas of research is making neural networks more efficient. Current large language models require enormous computational resources to train and run. They consume vast amounts of energy, limiting who can develop and deploy them. Researchers are working on techniques to make networks smaller, faster, more efficient, while maintaining their capabilities. One approach is model compression, taking a large, well-trained network and making it smaller, without losing too much performance. Another approach is developing more efficient architectures from the start, designing networks that can learn effectively, with fewer parameters. And there's research into specialized hardware, chips designed specifically for neural network computations, which could make training and inference much faster and more energy efficient. Another active area is improving how networks learn from less data. Current systems often require millions or billions of examples to learn effectively. But humans can learn from just a few examples. Show a child a couple of pictures of a new animal, and they can recognize it. This ability, called few-shot learning, is something researchers are trying to replicate in machines. Few-shot learning would make AI much more practical. Instead of needing massive datasets, systems could learn from just a handful of examples. This would open up new applications, domains where collecting large datasets is difficult or impossible. Medical diagnosis for rare conditions, recognizing objects in specialized contexts, adapting to new languages or dialects, all of these could benefit from few-shot learning. Related to this is the challenge of transfer learning and generalization. Current systems often struggle when they encounter data that's different from their training data. A network trained on photos might fail on drawings. A language model trained on formal text might struggle with casual conversation. Researchers are working on techniques to make networks more robust, better at generalizing to new situations. One promising direction is meta-learning, or learning to learn. Instead of learning a specific task, a network learns how to learn new tasks quickly. It develops general learning strategies that can be applied to new problems with minimal data. This is still early research, but it holds promise for creating more flexible, adaptable AI systems. Another active area is making neural networks more interpretable and explainable. As we discussed, current networks are often black boxes. They make predictions, but it's difficult to understand why. For many applications, this is a serious limitation. If a medical AI recommends a treatment, doctors need to understand the reasoning. If a loan approval system rejects an application, the applicant deserves an explanation. Researchers are developing techniques to understand what networks have learned, to visualize their internal representations, to explain their predictions. Some approaches try to identify which features the network used to make a decision. Others try to find simpler models that approximate the network's behavior. Still, others try to make the networks themselves more interpretable by design. But interpretability remains a challenge. The more complex the network, the harder it is to understand. And there's a tension between performance and interpretability. Often the most accurate networks are also the least interpretable. Finding the right balance is an ongoing research question. There's also growing interest in combining different types of learning. Current systems often use just one approach: supervised learning, or reinforcement learning, or unsupervised learning. But the future might see more hybrid systems that combine multiple approaches, leveraging the strengths of each. For example, a system might use unsupervised learning to discover features, supervised learning to recognize patterns, and reinforcement learning to optimize behavior. Or it might use transfer learning to adapt knowledge from one domain to another, then use few-shot learning to quickly adapt to specific tasks. These combinations could enable more capable, more flexible systems. Another direction is developing AI systems that can learn continuously, adapting to new information over time. Current systems are typically trained once, then deployed with fixed weights. But the world changes, and systems that can't adapt become outdated. Continual learning or lifelong learning would allow systems to learn from new data without forgetting what they already know. This is surprisingly difficult. When a network learns new information, it often overwrites old information, a problem called catastrophic forgetting. Researchers are developing techniques to prevent this, allowing networks to accumulate knowledge over time, just as humans do. There's also research into making AI systems more robust and reliable. Current systems can be fragile, failing in unexpected ways when they encounter situations outside their training data. They might make confident but incorrect predictions, or be vulnerable to adversarial examples, inputs specifically designed to fool them. Improving robustness is crucial for deploying AI in safety-critical applications. Self-driving cars, medical diagnosis systems, financial systems, these all need to be reliable, to fail gracefully, to handle unexpected situations. Research into robustness, safety, and reliability is becoming increasingly important. Looking further ahead, there's speculation about artificial general intelligence, or AGI, AI systems that can perform any intellectual task that humans can. Current AI systems are narrow. They're very good at specific tasks, but can't generalize to new domains. An AGI would be flexible, adaptable, capable of learning and performing across many different tasks. Whether AGI is possible, and if so, when it might be achieved, is hotly debated. Some researchers think it's decades away, or might never be achieved. Others think it could happen much sooner. The truth is, nobody knows. The path from current narrow AI to general AI is unclear, and there may be fundamental obstacles we haven't yet identified. But even without AGI, the capabilities of AI systems continue to expand. New architectures, new training techniques, new applications emerge regularly. The field is vibrant, active, full of possibilities. One thing is clear: data will continue to be crucial. As we develop better algorithms, we'll also need better data. More diverse, more representative, higher quality. The relationship between data and algorithms is symbiotic. Better algorithms can learn more from data, and better data enables better algorithms. There's also growing recognition of the importance of AI ethics and safety. As AI systems become more powerful and more widely deployed, ensuring they're used responsibly becomes increasingly important. This includes addressing bias, ensuring fairness, protecting privacy, and considering the broader societal impacts of AI. The future of machine learning isn't just about technical advances. It's also about how we choose to develop and deploy these systems, what problems we choose to solve, what values we embed in our algorithms. These are questions that extend beyond technology into ethics, policy, and society. As we look to the future, it's worth remembering how far we've come. Just a few decades ago, The idea that machines could learn to recognize images or understand language seemed like science fiction. Today, it's reality. The progress has been remarkable, and there's every reason to think it will continue. But the future is also uncertain. New challenges will emerge. New limitations will be discovered. The path forward isn't predetermined. It will be shaped by the choices of researchers, developers, policymakers, and society as a whole. What we can say with confidence is that machine learning will continue to evolve. New techniques will be developed, new capabilities will emerge, new applications will be discovered. The fundamental process of learning from data, discovering patterns, improving through experience, will remain. But how it's implemented, what it enables, and how it's used will continue to change. The future of learning, both for machines and for our understanding of how machines learn, is bright. There are challenges ahead, but also tremendous opportunities. And as we continue to explore, to experiment, to discover, we'll unlock new possibilities that we can't yet imagine. Chapter 10. The Bigger Picture. As we bring our exploration to a close, let's step back and consider the bigger picture. We've journeyed through the mechanics of how artificial intelligence learns. From neural networks to backpropagation, from training processes to real-world applications. But what does it all mean? What are the deeper implications? What can we learn about intelligence, about learning itself, about the relationship between humans and machines? At its heart, machine learning is about discovering patterns. Neural networks process data, find regularities, identify relationships, and encode these discoveries in their weights. It's a process that's both mathematical and mysterious. The calculations are clear, but the patterns that emerge can be surprising, even to the researchers who build these systems. This pattern discovery process connects to fundamental questions about intelligence. What is intelligence? Is it the ability to recognize patterns? To learn from experience? To adapt to new situations? Machine learning systems demonstrate some of these capabilities, but they also reveal how much we don't understand about intelligence itself. The relationship between learning and intelligence is complex. Learning is clearly a component of intelligence. Intelligent systems, whether biological or artificial, need to adapt, to improve, to acquire new capabilities. But is learning sufficient for intelligence? Can a system that learns patterns truly be considered intelligent, even if it doesn't understand what it's learning? These are philosophical questions that don't have clear answers. But they're important questions, because they shape how we think about AI, how we develop it, how we use it. If we believe that pattern matching is sufficient for intelligence, we might approach AI development one way. If we believe that true intelligence requires understanding, we might approach it differently. What's clear is that machine learning has revealed new possibilities. Systems can now perform tasks that once seemed uniquely human, recognizing faces, understanding language, playing games, creating art. These capabilities challenge our assumptions about what machines can and cannot do, but machine learning has also revealed limitations. Current systems are narrow. They excel at specific tasks but struggle with generalization. They learn patterns but don't understand causes. They can be fooled by adversarial examples, fail on out-of-distribution data, reproduce biases from training data. These limitations remind us that we're still far from creating truly general intelligence. The relationship between human and machine learning is also worth considering. We've used many analogies throughout this exploration, comparing machine learning to human learning. Learning to ride a bike, learning to recognize animals, learning through practice. These analogies are helpful, but they also highlight important differences. Human learning is deeply contextual. We learn in rich environments with multiple senses, with emotions, with social interactions. We learn not just patterns but meanings, causes, purposes. We can learn from very few examples, generalize broadly, adapt quickly to new situations. Machine learning, in contrast, typically requires many examples, learns statistical patterns rather than meanings, and struggles with generalization. But machine learning also has advantages. It can process vast amounts of data, finding patterns that would be invisible to humans. It can work continuously, without fatigue. It can be replicated, shared, improved, systematically. The strengths and weaknesses of human and machine learning are complementary, suggesting that the future might involve collaboration rather than competition. This brings us to ethical considerations. As AI systems become more capable, questions about how they should be used become increasingly important. What should AI systems learn? What patterns should they discover? What biases should we work to avoid? What values should guide their development? These aren't just technical questions. They're questions about what kind of future we want to create. AI systems learn from data, and data reflects the world as it is, including its biases, inequalities, and problems. If we train AI on biased data, we create biased systems. If we want AI to help create a better world, we need to be thoughtful about what we teach it. The responsibility lies with us, the humans who design these systems, who collect the data, who choose the applications. AI doesn't have values of its own. It learns what we show it. If we want AI to be fair, inclusive, beneficial, we need to ensure that these values are reflected in how we develop and deploy these systems. This is a profound responsibility. As AI becomes more powerful, the choices we make about how to develop and use it will have far-reaching consequences. We're not just building tools, we're shaping the future of technology, and potentially, the future of society. But there's also something beautiful about the process of machine learning. It's a process of discovery. We set up the structure, provide the data, and then the system discovers patterns on its own. We don't always know what it will learn, what patterns it will find, what capabilities will emerge. There's an element of emergence, of complexity arising from simplicity, that's deeply fascinating. This emergence connects to broader themes in science and nature. Complex systems, from ant colonies, to weather patterns to neural networks, all exhibit emergence, properties and behaviors that arise from the interaction of simple components. Understanding how learning emerges from simple rules, how intelligence-like capabilities arise from pattern matching, helps us understand not just AI, but complexity itself. The study of machine learning also teaches us about learning in general. By building systems that learn, we gain insights into how learning works. We discover principles that apply broadly: the importance of feedback, the role of iteration, the balance between exploration and exploitation, the challenge of generalization. These insights can inform how we think about human learning, education, and cognitive science. As we conclude this exploration, it's worth reflecting on the wonder of what we've discovered. That machines can learn, that they can improve through experience, that they can discover patterns and relationships, is remarkable. That simple mathematical operations, repeated millions of times, can enable capabilities that seem almost magical, is extraordinary. But it's also worth remembering the human element. We still teach the teachers. We design the architectures, collect the data, choose the applications, interpret the results. Machine learning is a tool, a powerful one, but it's a tool that we create and control. The future of AI will be shaped not just by what machines can learn, but by what we choose to teach them, and how we choose to use what they learn. The journey of understanding how artificial intelligence learns is ongoing. New discoveries are made regularly, new techniques emerge constantly. Our understanding deepens over time, but the fundamental questions remain. How do machines learn? What can they learn? What should they learn? And what does this tell us about intelligence, about learning, about ourselves? These are questions worth pondering, worth exploring, worth discussing. As you drift towards sleep, let these ideas settle in your mind. The world of artificial intelligence is vast and fascinating, full of possibilities and challenges. And at its heart is this simple but profound process: learning from examples, discovering patterns, improving through experience. The machines are learning. And in learning about how they learn, we learn about learning itself, about intelligence, about the remarkable ways that simple rules can create complex behavior, that patterns can encode knowledge, that experience can lead to capability. So as we end this journey, remember, learning is a process, whether for humans or machines. It's iterative, gradual, built on experience and feedback. It's both simple and complex, both understandable and mysterious. And it's one of the most remarkable processes in the universe: the ability to improve, to adapt, to discover, to grow. The exploration of how artificial intelligence learns is far from over. New chapters are being written every day by researchers around the world, pushing the boundaries of what's possible. And as these systems continue to learn and improve, so too does our understanding of learning itself. So rest well, knowing that the machines are learning, that researchers are discovering, that the field is advancing. And know that you too have learned something tonight, about neural networks, about backpropagation, about training, about the remarkable process that enables machines to learn. The journey continues, both for the machines and for us. And in that continuation, in that ongoing process of learning and discovery, lies the wonder and the promise of artificial intelligence. Good night, and may your dreams be filled with the patterns and possibilities of machine learning.